positive ratio, that the ratio of how many things I am doing false positive among all the positive cases. So that means how many true positives are there and how many false positives are there. So this is the ratio between what we are doing it for the false positive cases. So when you go with this kind of a curve for a random flip and for a random classifier, what you will find is, so I want to find my true positive ratio to be 1 and the false positive ratio to be 0. So in a random flip scenario, you will get this kind of a line. However, your estimation should be giving more true positives than false positives. So effectively, we get such kind of a curve depending on the scenario. And usually people try to measure what is the area under this curve, and often told as AUC, or area under the curve. And as you can see, this area under the curve is basically 1 in ideal case, because here your true positive should be this, and it's 0.5 if you choose the random line, the random coin flip case, or I would say coin flip classifier, that it gives randomly. However, in practice, if you plot this one, it will not look like as you have seen. You can plot any of these false positive ratio, true positive ratio. Let's say this is the nominal. So sometimes you will see that it is like this. Sometimes you will see this is like this, and so on. So what does it signify? Suppose a model M1 does it this way and M2 does it this way. So what do you think is better? So see, M2 is better when there are low false positive ratio. M2 model performs better. M1 is better when there are high false positive ratio. So usually there are these trade-offs people have to make. First of all, false positive ratio versus true positive ratio. That changes whether I will choose M1 versus M2 depending on the scenario. Sometimes also you may find that accuracy is a misleading parameter in such a way that you get 85% accuracy when you have 30 test data. However, you get 75% accuracy when you have 1000 test data. So which you will take? This, you get an M1 model like this and your M2 model like this. So how do you categorize between M1 and M2, that which one is better? So just M2, as you can see that this, right, because of the much more training data, but it's a lesser accuracy. So if you have to think, you need to, so why I'm skipping this part is that it has a statistical correlation between the data distribution and the accuracy handling. So how the data is being distributed in this 30 and how the accuracy being handled here. And usually with respect to the class boundaries, people try to plot a random variable X, and let's say this is the true positive ratio and this is the false positive ratio. So let me just later. And suppose your actual class boundary line becomes this, then you can see that this factor here, this is actually true positive cases. This side is actually true negative cases. In between this is, so your class boundary is here, so this side is positive and this side is negative. In between this according to your class boundary is saying it positive, but it is actually being in the negative distribution wise. So this particular thing is false positive and this particular portion is true negative, sorry, false negative. So usually depending on this, people try to plot, simplify this factor and try to plot the ROC where the curve under this matters. So it looks a little bit of odd, but you do not have to do anything because you just call the functions and get it. And to give you a glimpses, the best, so this I covered this one from the Wikipedia because this is very nicely summarized in Wikipedia. So please go through the Wikipedia article I am showing you for that. So is this visible?
Yes,
Yes,
sir.
sir.
Yeah, so you can see that all the particular factors. So this is this false positive ratio. This is the true positive ratio, Tp by Tp plus Fn. False positive ratio is Fp by Fp plus Tn. And then you can see this ROC is this curve, and actually it looks mostly the random classifier, and you get better and better towards the true positive tilt. The area under the curve improves, and so it gets better. And finally, the thing that I have mentioned is this one, that there are two distributions of positive and
Yes,
negative,
sir.
and your
Actually,
random.
that is true negative. I was just saying the same.
Yeah, this side I mentioned wrong.
Yeah, false negative.
Yeah, it's true negative. Yeah, true negative, true positive, and false negative. Yeah. So I think if you go by this article, this is the best that summarizes the whole discussion. There are many other measures. Among them, I just only covered this recall and precision, and you can see there are many other measures people use. So recall, precision, and F-score are the primary measures that are being used. Okay, so that's so two mistakes as somebody
Sir,
pointed out. This is
FPA.
negative.
Yes.
Yeah, I'm coming to your question. And here this is true negative, true positive, false negative. Yeah, this is correct. Yeah, your question.
Sir, sir, just explain the meaning of FPR and DPR, like sense, like what
Oh,
they say.
okay. Let me explain it. So TPR is the true positive ratio, right? So how many of them is correctly being classified as positive by your classifier divided by the total number of positives in the test data. See, how many of them are correctly classified, how many of them are wrongly classified, but actually in the test data these are positives, which are Tp plus Fn. Look at the confusion matrix. If the actual case is yes, then these are the things that you are classifying correctly, these are the things you are classifying wrongly. So your true positive ratio is A divided by A plus B. That's what I resulted here. This is a recall itself, nothing else.
Okay, so sir, this curve is for like same algorithm. We are changing the parameter and making different models and comparing them.
Well, that is one thing, and also you are also using different algorithms. Maybe you are classifying a decision tree and neural network. You are comparing which is good. Okay. Both things can happen. So as you said that we may, for let's say linear classifier, we may change our algorithms or the weight and can get a different lines, right? And try to compare this. Or we may try to compare between this perceptron versus the decision tree, which is better. Right?
Okay, sir. Right.
Both things could
So,
happen. But yeah.
can you go on the last page?
Mm-hmm.
So here the area for true negative and true positive, the area is overlapping, right? So how
Which one? This curve or this curve?
last
Which one?
last below
This one.
last, yes sir.
Yeah.
The
No.
area is
This is particularly the definition. So let me show you the definition. You read this one. This will be clearer for you. The definition says that this is a probability density where f1x belongs to the instance that says class is positive and f0x for the negative. So f1x is the right side Gaussian and the f0x is the left side Gaussian. So your true positive is basically the area within f1x, and the true and the false positive ratio is the area under F0x curve. And your class is actually this line. Your class is this line. Your predicted class boundary is this. The right side is plus and the left side is minus. Okay. And depending on this threshold functions that you are doing, it is actually changing this point in the ROC curve here and there. Okay. Just have a go at it. It's not very difficult, and it's also empirical. So, I mean, you do not have to bother. You just have to call the functions, and it will automatically be done for you. But underlying principle wise, it happens this way. Good. So that's the end of supervised learning in a traditional sense, though we will revisit back again when we go for ensemble techniques and dimensionality reduction. How do we reduce the dimensionality? But primarily the basic model wise, this is what we do and this is how we compare and reason about. From tomorrow's class onwards, we will dive down deeply into the theoretical aspects of learning. So I also request you to refresh our second lecture, which I ended with the feasibility of learning, where I said that the generalizations of something we could probably learn is classified by a boundary. We will try to generalize that how better we are learning, and we will try to figure out certain theoretical parameters through which we could estimate or we could judge the learnings and see the biases, variances, and all that. So next 2 weeks will be more theoretical, but I will try to give you the intuition and then draw the theory. As I always believe, it's first the intuition and then the theory is backed up with that. So with that, let me stop today's class. If you have any questions, I can answer. Otherwise,
Sir, I have a question. Can
Yeah.
you go to the slide 4?
Okay.
Sir, in stratified sampling, we are taking the data, we are considering the test data and whose level are known, right? So that's how we are saying this is yes or no. And then in case of stratified sampling, we are not replacing them in training data, but in case of bootstrapping, we are replacing them into the training data, right?
No, nothing here training. See, everything,
Okay.
it's a method of testing your classifier.
Okay.
So if you are given testing data with level, that is the ground truths you know, then you can test. If you are not given, you need to segregate out a part of the training data for keeping it for testing.
Okay.
But everything is testing data here. Nothing
Then,
is
sir,
of the
what is
training.
the difference between stratified and bootstrapping? That I'm
So
not
in
getting.
stratified sampling, your randomizations or collecting this randomly collecting data from the strata does not involve replacement. In bootstrapping, we use replacement also.
Okay, we are replacing where? Means on the.
Once you take out a data from a strata, so the number of data from that strata is reduced by 1 in stratified, but in bootstrap, I also keep that in the next time I randomly pick up something.
Okay.
Okay, so it may be there is a probability that in bootstrapping you get two similar data.
Okay.
That's the difference. All these stratified and bootstrap, this kind of strata-based sampling, I will again revisit when you go for ensemble techniques validations or estimations of ensemble techniques.
Okay.
Sir, in holdout, we are taking the data randomly. So what is the difference between random subsampling and holdout?
No. I am saying random subsampling is multiple times doing the holdout. It's not a different. It's just multiple times you are doing the holdouts.
That is what we're doing in cross validation, k times.
No, but it's a fractional split and it's a constant split. The name differs. You know that name differs. Ultimately, it's a split. It's a fractional split is called a holdout, and a constant partition split is called a cross validation. Randomness with respect to the elements that get puts in here. Here the randomness is with respect to the partition that you choose for testing, not the elements inside a partition gets changed. Get it?
No, sir. Confused.
See, you can partition. Let's say you have 10 data. Okay. You can partition it 2/3 and 1/3. Let's say you have 9 data. You can partition 6 and 3. Right?
Yes.
In one kind of such partitioning, you can put first 6 data and last 3 data in different in test. In some other randomization, you can put in the first place 1, 2, 3, then 6, 7, 9. For the test, you can put 4, 5, and 8.
Yes.
So that means my partition size are 2. One size is 2/3 elements, one size is 1/3 elements. But the elements inside the partition can be randomly and it can vary. Agreed?
Yes, sir.
That's holdout.
Okay.
K partition cross validation is you partition K and keep the elements inside it as fixed. But choosing which partition to keep it as a test is random. Got it?
Okay, sir.
See
And
here, let's say you are partitioning the same 9 data into 3 partitions. So 1, 2, 3 is the first partition, 4, 5, 6 is the second partition, 7, 8, 9 is the third partition. I will not change the data inside partitions. Where in holdout, I was changing it, right?
okay.
Here, I can take the first partition as test, rest 2 as training. I can take the second partition as test, rest 1 and 3 as training. And I can do the third partition as test, 1 and 2 as training. This is the randomizations in cross validation. Otherwise, the randomization in holdout with respect to the data that I put in each partition, because my partitions are 2 only.
Okay, sir.
Okay.
Yes, sir. So I have another doubt in last slide.
Yeah, please.
So here, like we are drawing this graph, like so for different test set, we are taking TPR and FPR and then drawing this graph for a single model.
Different test set means confusion matrix is for the M test data. That is the test data that is given to you.
So for a single model, we have one test data.
For every model, you have one test data.
So how we are getting the different TPR and FPR for single model?
We are getting the different TPR and FPR means, I mean, what is where are you getting it different?
So in the second graph, we have like graph between TPR and FPR. So we have different value of TPR and FPR. Then we are drawing this M2 graph for model 2. Okay. So how we are getting this TPR, different TPR and FPR value to draw this graph?
Oh, that is with respect to the number of data. That is with respect to the number of data. So here, see, what does it mean? Suppose this is 0.1 and let's say this is 0.5. So what does it mean? It means TPR is 0.5 and FPR is 0.1 in this point, which means this many. So suppose at this point you have seen M1 number of test data. In M1 number of test data, your FPR is 0.1 and your TPR is 0.5 with M1 number of test data. If your test data be more, it could fluctuate.
Okay. So sir, the like
just see the learning curve. This one. How do you put the accuracy with respect to your sample size, right? Here also we do the same thing.
Okay, sir. Okay. So the on 0, we have like on 0 side, we have minimum number of test data.
Yeah, nothing. One maybe zero test data. I mean, we have not started the testing on 0.
Yes, yes. So sir, to choose base model, we should look toward 1 side, right?
Yeah,
because it has maximum number of test data.
The more area under the ROC curve is, the better your model is.
No, we are increasing the test data, so the graph is changing. So for better better choice of model, we should look for one like point where which graph have more area.
No, at the end, you are only given a fixed number of test data, right? So it will only be a particular value. If I have varying number of test data, I could look it as a graph, but ultimately at the end of the day, what you do, you have a classifier C, ensure me over M, how is your TPC and RPC ratio? You will get a value, right? Our claim is if that classifier behavior with respect to the number of data is more towards the TPR side, that is the area is much towards the one side, then your model is good. But at the end, after you test, you will get a point only.
Okay, sir, got it.
So the classifier that if you are given with, if you know the unknown function, if the classifier behaves like this, it is better than it behaves like a random coin flipping kind of thing. Right? But given the test data, you will get only 1 point in this particular ROC line.
Yes.
Think a little. Yeah.
Yes.
Okay. Thank you. I think we are more than 14 minutes up. So let me stop recording and